Hello, hi to everyone. Next, we are moving to the second part of the video, second lecture of a special diodes. So that is a topic is tunneling effect. So before going to the tunneling diode, we are going to discuss about the tunneling effect, what exactly it is. Then we are moving to the so tunneling effect. So look at here. In case of normal diode, in case of normal diode, uh, you know the doping level is lightly doped or lightly doped compared to the GNR diode or tunneling diode. Normal diode lightly doped. Whenever it is a lightly doped, for example, it is a germanium. In case of germanium, what is the voltage, minimum voltage to required to break down the junction? The forward bias case 0.3 volt. In case of silicon, it will be 0.7 volt. That is the minimum voltage required to turn on the diode. Okay, that is a case in case of normal diodes. So the depletion layer is also, the depletion layer is also very high in case of normal diode. The depletion layer is also very high. So coming to the here we have a n-type material. In case of n-type material, in the conduction band and valency band, two bands are present. In that two bands, the n-type material have a more number of electrons in the conduction band. In case of p-type material, more electrons in the valency band, more holes present in the valency band, less electrons present in the conduction band. Now my in the tunneling effect, I'm increasing doping level. So doping, very high doping. So doping level increases. It is a very high doping. Whenever you are increasing the doping level, very high doping, heavily doped, more than the GNR diode. In case of tunneling effect, tunneling diode construction, more than GNR diode, we can doping level is very high. Whenever doping level is very high, it means 1,000 times more. Usually it is a normal diode. For example, it compared to the normal diode, it is 1,000 times heavily doped. Okay, that is a point you need to remember. Whenever it is heavily doped, what will happen? The conduction band, a number of electrons, more free number of electrons will be increases. In case of p-type material, more number of free holes are present. What we call in the valency band, it is available whenever your doping increases. All of you following? So whenever in this particular case, the depletion layer, coming to the depletion layer, is very thin. Okay, depletion layer. What is a depletion layer in normal case? It is okay. It is a not thin or not wide, moderate range in the normal diode. But in the case of tunneling diode, the depletion layer is very thin, because your doping level is increases 1,000 times more than the normal diode. So whenever depletion layer in very thin, it is about, the thin of depletion layer, thin of depletion layer is about 0.00001 mm. Okay, clear? So very thin layer. So that whenever these particular conditions occurred, very small amount of voltages, even in case of you are using germanium to construct this particular tunneling diode, even less than the 0.3 volt, it is also conducting. That means turn on. So conducting, that means that punch through happen. So punch through, so it is going to be conducted very high speed. So got my point? So that's why this particular mechanism, you call it as a tunneling effect. This particular mechanism, okay, tunneling effect. We'll see what exactly the tunneling, and with the help of the depletion layer and then applied voltage. And if you clear about the doping level, very high doping level, very thin depletion layer. That's why this particular tunneling effect is possible in these particular conditions. So let us see one by one. So in this particular case, the first diagram, look at it, everyone look at the first diagram. First of all, I am going to not giving any biasing. That means any external force, so no biasing. no forward bias. So in the normal condition, so there is no forward bias, we'll see. Without having any forward bias, so conduction band, this particular conduction band in n-type material, more number of electrons will be present because it is highly doped. And then this is a valency, this is a conduction band. In case of p-type material, this is a conduction band. In case of valency band, this type of holes are present. There is no tunneling because no forward bias. There is no forward bias, there is no tunneling because this alignment, see here, this alignment is not exactly the same. So this alignment is not exactly the same. So the p-type material is somewhat upper, and n-type material somewhat downwards towards in this particular diagram. All of it clear? Tunneling is not happened, both are not aligned. So now here see, look at in the second case, whenever it is biasing, small biasing, so small forward biasing. So in the second case, small forward bias. Whenever it is a small forward bias, here, small forward bias you are applying. That means that for a particular tunnel diode, we are giving small forward bias voltage less than the peak voltage. Whenever you are giving the small forward bias voltage, what will happen here? This particular this particular n-type material conduction band is downwards and reach to the valency band of p-type material. So see here, both are aligned. So whenever you are applying the small bias voltage, so this particular electrons jump to this particular conduction band to this particular valency band of p-type material. Though it is a simple, so some tunnel will be formed. This is called as a tunnel. So that's why it is called as a tunnel diode. Some tunnel is provided to pass this particular electrons easily. Okay, that's why it is called as a tunneling effect. So it is easy to transfer the electrons from the valency conduction band of n-type material to valency band of p-type material. So this will happen very easily. So it is a small forward bias. What will happen if you are further increasing the applied voltage? So that is a next case. Your bias further increase. So bias further increase. So what will happen? You will see. If you are further increase the bias voltage, what will happen? This particular n-type material, the valence conduction band further downwards below. Okay, that means that these both aligned are deviated. It is above the this particular valence conduction band of valency band of p-type material above this particular conduction band. Okay, that means that both are not aligned. So it is a current going to be, in this case current going to be increases because conduction is taking place. In this case whenever we are moving downward direction, current going to be decreases. That means that it is a negative region. Okay, negative resistance region. So we are increasing the further voltage, that particular portion we are calling it as a negative resistance region. We will discuss the characteristics now. Still everyone is clear about the tunneling effect, right? Then we are moving to the tunneling diode. So very important. In 2016 question paper, they are asking about the symbol for tunneling diode. So everyone remember that this is a tunneling diode symbol. So this is a symbol you need to remember. So tunneling diode, this is also symbol for representation. So this is the symbols for tunneling diode. So we'll see already we saw the construction. We'll see once again the construction points, repeat, and then we'll start the characteristics. Okay, in the construction point of view, already I mentioned it is a heavily doped. So how many times it is heavily doped? 1000 times more than the compared to ordinary diode. So heavily doped more than 1000 times. Clear? Next, another thing, if you are heavily doped, so three things will be happen. The first thing, it reduces the depletion layer. Just now I mentioned it reduces the depletion layer. Depletion layer width is reduced. That is the first advantage. Okay. Second thing is happened for heavily doped in the construction of tunnel diode. It reduces the breakdown voltage. The breakdown voltage is reduced in the forward bias condition, in the very small the breakdown voltage. So sometimes it is approaches to zero also, the breakdown voltage. So that means very high speed switching purpose. It can be used as a this particular diode for switching purposes. And then third point you need to remember, it produces a negative characteristics, that is a VI characteristics is negative case also. Okay, these are the things happened for this particular tunnel diode because of it is heavily doped. So let us see the negative characteristics and remaining things. So see here. So for characteristics of VI characteristics of tunnel diode. So the characteristics between applied voltage versus the current flowing through the tunnel diode. So initially we are giving, for example, this is a tunnel diode. So this particular diode, I am applying some small voltage. For example, 0 voltage you are applying. What about the current flowing through the tunnel diode? 0. So whenever voltage increases further up to the voltage of peak voltage. Whenever it reaches to the peak voltage, apply voltage is reached to the peak voltage. So diode conducts maximum current. That current you are called it as a peak current. Once it reaches to the peak current, that means that already mentioned in the previously, conduction band of n-type material is maximum aligned with p-type material valency band. So the conduction band and valency band aligned horizontally whenever it reaches to the peak voltage, whenever you are applying to the peak voltage. Otherwise, just recall here that peak voltage condition occur whenever we are reached to this particular condition. Whenever n-type material valency band and p-type material n-type material conduction band, p-type material valency band, both are aligned together, then it is a condition the peak voltage as well as peak current will be occur. Peak voltage and then peak current will be occur. So this is the condition. So after that, what will happen? See here, I am trying to increase further voltage. This particular voltage I am going to increases further. Whenever I am increases further this particular voltage, what will happen? The n-type material, the conduction band below and downwards, and valency band of p-type material upwards. So the both are not horizontally, both are deviated. So both are not exactly horizontally. That means that the conduction, the electrons from tunneling the electrons is reduces. That means the current flow into the tunnel diode reduces. Okay, it is reduces further up to the valley point. Valley point is nothing but a minimum voltage. After that, that is a minimum, valley point, that is a minimum current offered by the particular this particular tunnel diode. That is call it as a IV. That voltage is a VV, valley point. After that, again it is start again tunneling effect. Again started tunneling effect. Again it is increases the current. After reaching the peak value, again it decreases the current. This process is repeated further, say one by one in particular time period. This process is repeated. The important point, everyone remember that negative resistance region. This is a negative resistance region. That is means that the slope is negative from A to B. So A to B is a negative resistance region. This is a main advantage of this particular tunnel diode using for different applications. Okay, so all of you got an idea about tunneling VI characteristics of tunneling diode, right? Already tunneling theory I already explained to you how exactly the peak voltage, how exactly the valley point, everything. Now we are moving to the parameters. So diode parameters we are going to discuss. What are the parameters we have? The first parameter is a negative resistance. The first parameter is a negative resistance, that is called it as a Rn. So the negative resistance Rn means the change in voltage, the change in current divided by change in voltage. So the negative resistance Rn is equal to minus change in voltage divided by change in current in this particular negative slope. So this particular value depending upon the semiconductor material. For example, you are using the germanium. We'll get to some other value. Its value is nearly minus 10 ohms to minus 200 ohms in general. The values based on this value changes based on the different type of materials. So after that, second parameter we have to remember the ratio of current IP divided by IV. The ratio of current IP divided by IV ratio. It is also very important in the tunneling diode effect. So this ratio, for example, will take this is the most important factor, particularly in the computer application, switching on and off purposes. As a negative resistance of a diode, the first silicon diode will take first of all silicon diode. For the silicon diode, IP by V ratio, IP by for silicon diode, IP by IV ratio is 3:1. Okay. There is negative resistance, approximately Rn value, negative resistance value minus 220 by IP. Okay. That is the change in voltage, 220 by minus 220 by IP. That is a silicon. For example, germanium, the IP by IV ratio. For example, germanium IP by IE ratio is 6:1. So it is about the germanium. The negative resistance is about Rn is equal to minus 120 divided by IP. That is for negative resistance. So in case of gallium arsenide, why I am giving all these static parameters, it is a chance is there in the examination. So IP by IV ratio for gallium arsenide is 10:1. So and a negative resistance is equal to the silicon diode. So same as silicon diode, it is a negative resistance region. Next we are moving to the IP by IV ratio for gallium SB, GaSB. So that will be 12. IP by IV will be 12:1. So it is a low resistance of given Rn is equal to minus 60 by IP, the negative resistance. Okay. So this particular diodes having low noise. The main advantage is it is having low noise. In this particular region, you can use as a very high switching operations. Okay. Next we are moving to the another important point, equivalent circuit diagram. So equivalent circuit. So it is one of the important question in the 2018 paper. I guess they provided some circuits, identify the which is the diode, this particular circuit equivalent circuit. So here LS, equivalent circuit diagram for tunnel diode, and then this is a capacitor, and then this is a resistor minus Rn, and then this is a resistor source resistance. This is the equivalent circuit diagram for tunneling diode. Okay. So tunneling diode equivalent circuit. Next we'll see diode biasing. So this particular biasing we can choose as a particular let me draw the diagram for that. So characteristics. So in this particular characteristics, this is the way the characteristics of tunnel diode. It is similar to the UJT, uni-junction transistor. We'll discuss that in the transistor case. This is 0. This particular point is Q. Whenever it is a biasing this particular point, so we can act as a oscillator. So where you biasing this particular diode, you can choose the particular applications. For example, we can use it as a normal diode. We can bias these particular characteristics here initially. We can bias, it can be used as a normal diode. So based on the biasing is nothing but based on that where you this particular diode is using, based on that you can bias. After that we will see applications. So already mentioned, very important these applications. So applications are, the first application we can use it as a high speed, ultra high speed switch. Ultra high speed. Okay, so very required ultra high speed switching, we can use this particular diode. And the second thing here, logic memory storage devices. The application is logic memory storage devices. Third point is microwave oscillator. Microwave oscillator. This is about the applications. Next, advantages we'll see. So I will tell you advantages overall. No noise. Low noise means it, whenever you are operating, the noise present in that particular diode operation very less. Low noise, easy of operation, high speed and low power. Okay, insensitivity to nuclear radiation, that is very important. In case of nuclear radiation also, it can be withstand. That is advantage. The only disadvantage here, it can be only operated 1 volt or less. Only this is a one disadvantage. As well as being two terminal device, it cannot be isolated. It cannot be isolated from the input and output. That is another disadvantage. Everyone is clear about the applications and advantages and disadvantages. Then we are moving to the tunneling diode as an oscillator. With that, we are going to end of tunneling diode explanation. Then we are moving to the varactor diode and pin diode, as well as the Schottky diode, step recovery diode, and then Mister in the next video. Okay, so we will complete the diode, tunnel diode as a oscillator. We'll see. So tunnel diode act as a oscillator. So just look at this particular diagram. We design this particular resistor based on that way operating point related to the particular diode act as an oscillator. Initially, we are switch is off state. Initially, this particular switch is off state. Now, what we have to do that? So now what we have to do that? Whenever we are increasing the voltage up to where you need to operate it in this particular tunnel diode act as oscillator at the point of the negative resistance region. For example, I am going to operate this particular tunnel diode in the characteristics after value peak point of voltage. This is the point I am going to choose that. So that means that whenever I am switch on the power supply, after reaching this particular voltage, particular supply voltage reach it to the above the peak value. Once you switch on the power supply, what will happen? This diode, once you are applying the peak voltage, once you are applying the particular voltage, that is a biasing voltage at the Q point in the negative resistance region, tunnel diode act as a conducting, but in the negative resistance region. Whenever in the negative resistance region, current going to be decreases up to value point, that is a IB. So in that particular case, again switch is off state. Okay, whenever the switch is off state, again switch on the power supply after reaching the another cycle negative resistance region. Again the point will be, again it is biasing and then it is conducting in the negative resistance region. That means that it is a keep on like oscillations. In that particular case, the oscillations will be like that. So your each and every time oscillations will be generated like a sawtooth waveform. So this is like a oscillator. All of you clear? All of you get the idea about the how tunnel diode act as oscillator? This is a way. But in the examination, it is objective examination. They will give the options like that. Which are the following diode can be used as an oscillator? They will provide the different options. One of the option is tunnel diode. So tunnel diode act as an oscillator. This is the working condition. Then I will give some modification diagram for this LC, that is a tuned circuit. So it is connected parallel with the this particular combination parallel with the R1. This is R2 is a fixed resistance. This R2 is decided that the operating voltage of the particular diode. R1 is tuning the frequency. So in this particular case we are going to give whichever the operating point you want to operate in this particular circuits, automatically it is done, we can generate the oscillations. Okay, this is about tunnel diode as a oscillator. Okay, so this is about the complete explanation about tunnel diode, around 25 minutes. That is enough. You may expect some of the questions from this particular tunnel diode also. So thank you.